In this unit lesson, we're going to talk about 5 of the 8 statistics curriculum, Inference. This unit is very vocabulary heavy, so I would suggest paying close attention to vocabulary in big detail. However, the topics of this unit would be confidence interval and hypothesis testing of proportions, and in general, inference about proportions. Let's start off with the central limit theorem. It just states as the number of data increases, the distribution becomes more and more normal. So it means that as we increase, for example, our sample from 10 people to 100 people to 1,000 people, we'd expect the shape of our data to become more and more normal. It is similar to the law of large numbers in the previous unit. The law of large numbers was that as the number of trials increases, the probability of an event hones in or gets closer and closer to one number. The next is sampling distribution, which is all of the proportions from all the possible samples. Sampling variability is just the variability you expect in your distribution. Your standard error is a standard deviation of the sample. You'll see me interchangeably use standard error and standard deviation of the sample. The confidence interval is just a statistical interval to determine if a given value is significant or not. We will go into great detail with confidence interval further in this lesson. The margin of error is just the extent of error on either side of the interval. So you might have heard that when governments give you the population statistic, they will say the population is, let's say, 1 million with a margin of error of 5,000, which just means that they think the population is 1 million, but they could be wrong with about 5,000 people up or down. So they think that the population lies within 5,000 of 1 million on either side. So 1 million plus 5,000 and 1 million minus 5,000, sorry. A hypothesis test is a statistical test to determine whether a given value is significant or not. Again, we will go in detail with the hypothesis test. As you can see, confidence interval and hypothesis test are just statistical inferences to determine how significant or whether a value is significant or not. Alpha, or significance level, represented by the Greek letter alpha, or it looks like a A, is the level at which if the p-value is below, you reject the null hypothesis, or probability of rejecting the null hypothesis when the null hypothesis is true. So we will get into big detail, but if you didn't understand null hypothesis, no worries, you will understand it by the end of this lesson. Now, type 1 and type 2 error are very simple, but it does deal with null hypotheses again. So type 1 error is just incorrectly rejecting the null hypothesis, and type 2 error is incorrectly failing to reject the null hypothesis, which just means is a false positive. Now, the power of a test is a probability that we will correctly reject the null hypothesis. We're going to move on to confidence intervals. So confidence intervals, as stated above, is just a way to determine how significant or if a value is significant or not. There are two types, which are one proportion and two proportion, which we will discuss in this unit. So one proportion is used to test whether the given proportion is significant or not. Significant to what? Significant to the population proportion. So the standard error is written as this. So if you remember it, when we talked about the probability unit, we referred to P as P, which is the probability of an outcome, and 1 minus P as Q, which is 1 minus probability of an outcome. So similarly here, P refers to the proportion of whatever we're testing, and over here is Q, which is 1 minus the proportion of what we're testing. Now, confidence interval is generally given as this. It's your estimate plus or minus your margin of error, because your margin of error can be positive or negative firstly. So you want to check whether you want to give an interval between which you expect your values to lie within. This is what you consider it. So it's P hat plus or minus Z star. That's not Z. So it's Z star multiplied by your standard error, which comes from here. Now, Z star, right? We need to talk about Z star. Firstly, it is Z star, right? So Z star, which is found from the normal model corresponding to the specific confidence level. So Z star is this value we assign based on our confidence level. So the higher z star is, just means the more confident you are. But as you can see, if z star increases, so does your margin of error. This whole section over here refers to your margin of error. Star times SE, or your standard error, is your margin of error. Now, this small margin of error means your interval is more precise. It just means that your z star is low, right? Because your margin of error is low, which means that your confidence level is like 1%. You're 1% confidence that it's here. And for a large margin of error, your interval is less precise. This may be a bit counterintuitive because you'd expect a large margin of error to mean that you're less confident. But it is in fact that a smaller margin of error means you have a lower z star, which means you're less confident. You have a confidence level of 1%, for example. Now we need to talk about z star, p, and p hat because I did use all of these. Now z star is, firstly, let's define the z star. We defined it above as something you receive from the normal model. But if I say, if I want a 95% confidence level, how to find z star is, either you can go and look at the table of values in your formula sheet, which your teacher will definitely talk about, or you can do inverse norm of 0.95, 0, 1, or you could do 0.05. This could give you a negative answer or positive answer. Doesn't matter. When you put it into margin of error, you will get the same answer. Now what is p? P is your observed value, and p hat is the sample proportion. So what does it mean by observed value? This just means your population proportion. So if, let's say, these could line up, p hat and p could definitely be equal to each other, and they can definitely be not equal to each other. But p means, what does the population say about your variable? What is the proportion of your population? P hat is based off your sample. Move on to two proportion, which is used to test whether both your proportions are significant enough. Now the standard error for two proportions looks very similar, but since there are two proportions, we label with the subscripts 2 and 1. It's just P1 Q1 over N1 plus P2 Q2 over N2. But the syntax is still the same. But instead of having P hat, we would have the difference of P hat. Now you have conditions. You can't just always use two proportion or one proportion testing. You have to figure out whether you can use it by some conditions. So our first condition is that NP is greater than or equal to 10 or approximately normal. We do that so that we know that there's no skewness in the data. The second one is that the test was conducted using an SRS, that each participant in the study or simulation or sample was found and had an equal chance of being picked. Next one is independence. Are all members of your sample independent of each other? Does person A's answer impact what person B says? You need to make sure that's important. And the last one is that N, or your sample, is less than 10% of the population. In my website, I have linked to a PDF that explains why this has to be the case. That's one of the conditions for one prop Z. It's that NP has to be greater than or equal to 10, and so does NQ, or N times 1 minus P. Now for two proportion, it's a bit more difficult. It's long junk, or both of the distributions have to be approximately normal. Now, what is all of this junk over here that I just said? It is your first proportion. That is this portion. N times your sample, what you got from your sample, and your first. So in this situation, it's going to be, from here will all be based off your first population, the proportion you got from your sample times 1 minus the proportion of your sample, and then from the second sample, the proportion from the sample times and 1 minus the proportion from the sample must all be greater than or equal to 10. So similar to this, but this dealt with n times the proportion of the population. This one is n times the proportion of the sample. Now for 2-prop, you just have to remember everything from one proportion, and then you just write both. So both have to be SRS, both have to be independent, and also independent of each other, and both n have to be less than 10% of the population. So knowing these three will help you get all the conditions for both 1-prop and 2-prop, except for this one, where you have to realize that in 1 proportion it is based off your population, and in 2 proportion it is based off your sample. The conditions, or if the question says assume conditions are met, you can now proceed with your confidence interval. So step 1, first figure out, right? That's the best thing to do. Figure out if it's 1-prop, or 2-prop, right? Sorry. The second one is check conditions, which is very simple. Now in the first step, you can also write down which prop, right? Which proportion is it? Is it 1-prop, 2-prop? So you'd write down, if it was 1-prop, you'd write 1-prop Z interval, or 1-prop confidence interval, 2-prop confidence interval. Then you check your conditions. If they say conditions are met, don't write it down. Then write down formula. That's what they count as step mark. So what you write down as your formula would be the confidence interval formulas. The next one is find the confidence level. So which would be Z star. So if they ask for 95, you find what that is, and you write down Z star equals inverse norm of 0.9501. Next is step 5, which is conduct the test, or conduct the interval. So if you're in TI Inspire, these are what the controls are. You'd go menu 6, which would be menu statistics confidence interval, and then depending on which one you're looking at, and then you input the number of successes. So number of successes will not be a proportion. You would have to find how many actual successes. It'll be a whole number. If, however, your proportion is some odd number and you get your successes as a decimal, you should round down, and then you write down your number of trials and your confidence level. So step 6 would be write down your interval in the form lower bound, comma, upper bound, and draw a picture and conclude. So for example, if we got something like 0.1, 0.5, so this would be how I'd conclude. 0.1, 0.5, we are followed by confidence level percent certain that the true proportion of whatever variable you have lies between 0.1, 0.5, which is our interval. Now when I say draw a picture, I just mean draw the normal model and locate where your interval lies. A good example of a model. You shade in your area, which would be your interval, and write down the percentage, followed by what your values are. They just use negative 1.96, but if your values were 0.1 and 0.5, you do that and label where 0 is. So if they give you a value, and if the value is outside your interval, we say it is statistically significant. So just remember, since 0.1 and 0.5, that would be your interval. Since 0 is outside that, we'd say 0 is statistically significant. There's another test that we can use to determine how significant, or if a value is significant or not. It contains both a null and alternate hypothesis. The null hypothesis is where the proportion from the traditional value. The alternate is, as you can maybe guess, where the proportion is some change from the traditional value. So we can, what do I mean by some change? So in brackets I'll put some change would be greater, less than, or not equal to. Not equal, right? So that means we can say that our alternate is that the proportion is greater than what our null says. It is less than and it's not equal to. If the alternate hypothesis is a not equal to, then we call it a two-tailed test, and we must multiply the p-value by 2. Again, we will come to p-value in a second, but let's just finish this. Otherwise, it is a one-tailed test. So what do I mean when I say one-tailed and two-tailed? One-tailed test. It is where, as you can see, our p-value is just in one corner, whereas in a two-tailed test, it occupies 2 areas. So over here, it counts as 0.05, and here as well 0.05. So it counts for a total of 0.1, and therefore our middle values obtain this area of 0.9. Confidence intervals, we have one proportion and two proportions for hypothesis testing. So one proportion is used to test whether the given proportion is significant enough. Again, your standard error will be the same thing. It's p, q over n, all square rooted. Conducting the test. Now this is what your null hypothesis looks like. This is your p, which you observe from the population, and it is equivalent to some value. You can range, and most of the times it ranges from all the time it ranges from 0 and 1. Sometimes it can be 0, sometimes it can be 0.7, it can be anything. Your alternate, on the other hand, is determined by what the question states. So here in your null hypothesis, it would always have this equal sign. But in your alternate, it can be a not equal to, a less than situation, or a greater than situation. It can be any one of these, and it all depends on the question. Now we're going to talk about something called a z-value. The z-value is just your p-hat, which is your sample value, minus your population value, all divided by your standard error. Now that will help you determine whether the sample proportion is significant or not. Now for two proportion, again very similar, standard error is no change, which is p1 q1 over n1 plus p2 q2 over n2, all square rooted. But when you conduct the test, your null is now this. It is the difference in your proportions equivalent to some value. It is your difference in proportions that is not equal to your value, less than or greater than in terms of your alternate hypothesis. The value for two proportions looks very similar to this for one proportion, but this time it's the difference in your samples minus the difference in population divided by your standard error. Sometimes, but not always, this p1 minus p2 is equivalent to 0. So then blocking that out, for example, would lead you with this as your z-value. I'm going to leave that in there for now. Now, using your z-value, you can determine whether your given value is significant or not. So using the z-value, you can determine whether or not, you can determine the probability that the value given, which is p hat, is significant or not. Conduct your test, the z-value will return a specific p-value. Now this p-value is what determines whether it is significant or not, and we will discuss it right here when we talk about conducting a hypothesis test. Firstly, as like the confidence interval, you need to figure out if it is one prop or two prop test, and state the test. So you have to state it is a one prop hypothesis test or one prop z test, or it is a two prop z test or two prop hypothesis test. Then, unless says otherwise, always check conditions. Students generally forget to check conditions because they're caught up in the remainder of the test. But this is one of the most important things you must remember, because if you don't test your condition, your test has no value. Next, write down the formulas. Again, this is what the AP exam counts as step marks. The next is you need to find z-value, right? that is this p which was given above. For example, in 2prop, this is what it was. Find that is because sometimes they will ask you in subsequent questions, what is the z value? And given that you already found it in the previous question, you can automatically write it down. The next one is conducting the test. So the reason I say TI Inspire controls is because in our school we use TI Inspire, and on the AP exam it is recommended. So you'd go menu, statistics, stat test, and then depending on which test you're using, remember it is z test for proportions, input your p hat, which is what the sample says, into p0, the number of successes which you're going to have to find. Again, when they give you proportion, you'll have to convert that into the number of successes and round down. Your alternate hypothesis and your number of trials. Alternate hypothesis would be your not equal to or greater than or less than. Please read that, as sometimes students will put less than when they should be putting greater than because of the way it's structured. Is to write down your p-value and conclude. So if let's say your p-value, for example, p-value less than 5%, you would say low p-value. This is how I wrote it in my exam. Low p-value, reject the null hypothesis, which is referred to like that. Insufficient evidence that your alternate hypothesis is true. Why do I put this in star? Is because you have to write down what it is. So if let's say your alternate hypothesis is that the proportion is not equal to 0.4, you write low p-value, you reject the null hypothesis, insufficient evidence that your, sorry, not alternate, your null hypothesis. Conclusion, you would always write it in terms of the alternate hypothesis. So you would put sufficient evidence that your alternate is true, which you can think about it as sufficient evidence that your null is false, but you would have to write it that the alternate is true. So if your alternate was that your proportion is not equal to 0.4, you write sufficient evidence that the proportion of whatever your sample is looking at is not equal to 0.4, sorry. Now if your p-value is greater than 5%, this means you got a high p-value, you would not or fail to reject the null hypothesis, and insufficient evidence that your alternate hypothesis is true. So you'd always like to write it in terms of the alternate hypothesis. So if you look at the difference between these two, you see low, high, reject, fail to reject, sufficient, insufficient, and then alternate is true. Why do we say fail to reject instead of completely saying it is correct? Because if we don't say that it's correct, because we don't know whether it's correct, we just know that it's not wrong. In statistics, just because you know something is true doesn't mean the opposite is true. You just have a feeling that that this is wrong. And why do I say 5%? Generally on the AP exam, your alpha level or significance level will be generally assumed that it's 5%. Unless said otherwise, 5% is always a good use. Now your p-value is what you receive from your test, from your hypothesis test. And it's very important because that's what helps you determine whether your value is significant or not. It generally ranges, actually always ranges from 0 to 1. So it's similar to like a probability. So if you want to think of it, if you're good with probability, you can think of it that your p-value is the probability that your number is significant. So if the probability is less than 5, there's a high chance that your alternate is true. That means that you're not equal or greater than. And if it's greater than 5%, means it's most likely that the alternate is not true. When we get to type 1 and type 2 errors in the next unit, where I will discuss it more in depth, we will also look back again on p-values. Unit 6 does deal with this testing, but in means and not proportions. I have 2 questions for you to try to see how much you've learned. One of them will deal with the confidence interval and the other one with the hypothesis test. First, let's deal with the confidence interval. Create a 97% confidence interval if the population proportion of people meters tall is 0.3. Sample of 200 people showed the proportion to be 0.4. Assume conditions for inference are met. So I'm going to copy the steps again so you know what to write. Let's figure out what test it is. So given that they haven't told us that that there are multiple populations, your sample of 200 people, we can assume that it's one proportion. So we're going to write it is 1 proportion z interval. Why interval? Because they said confidence interval. Now we have to check conditions. Over here it says assume conditions for inference are met. So we also have to write that down. Conditions for inference met given in question. Otherwise you can't say conditions for inference are met. That doesn't make sense. Where has it been written? Now for the formula. The formula, if you remember clearly, was formula for Q you could write 1 minus P. It is perfectly acceptable. Now you could go ahead and use in. You could put in for P hat 0.4 and then find Z star and all that. But this is good enough as your setup. Now we just need to find Z star, right? So we put Z star equals inverse norm of, they told us that it's 97%, so 0.97 comma 0 comma 1, which is equivalent to 880794. You can write all of this, or you could have cut it off at 1.88. Since the question is just one-fold, meaning it's not asking for inverse for Z star later in the question, you don't actually have to write this, but I think it's good. It's good practice. The next step says to conduct your test, so we're going to conduct that. So we go into menu and we do all of this. I'm going to take a screenshot of TI Nspire and put it onto this. Slight issue with the TI Nspire software, so I had to go into my calculator, but I had to first figure out what this X value was. So I just got 0.4 multiplied by 200, my confidence level of this. And I plugged it in into one prop Z interval, as you can see over here, and I got these values. So over here, as you can see, there's a lot of things going on. The title, C lower, C upper, P hat, M, E, and N. None of these are really important except for C lower and C upper. N is the number, is your number, or the number of trials. M is your margin for error. P hat is what you put in here. Not actually put in here, but it's what you got from your sample. Title doesn't matter. So you're looking at this. So your values come up to be 0.324826 and 0.475174. So now it's time to conclude. It says write down your interval in the form lower bound, comma upper bound, and draw a picture and conclude. So we're going to use this exact format. So my interval was this. So this is my interval. I'm going to make it to 3 decimal places. So round that up and round this. So 0.325, 0.475. Then we are, what is our confidence level? So 97%. We're 97% certain, or you could write confident, however confident you are, that the true proportion of people over 1.5 meter tall lies between the interval again, which would be this, which is, or lies between 0.325 comma 0.475, which is our interval. I also said to put a diagram, so I will quickly put that in and show you what I mean. Drawing, as you can see, I put my percentage in between here and my lower bound, my upper bound. If you wanted to, you could have definitely shaded this part in, but this is a very basic and easy drawing. You can whip it up in a couple of seconds, make your curve, and you're set. So this whole interval with the conducting of tests, the checking of conditions, the writing formula, all of this should get you your perfect points on this sort of question, provided you don't make any calculation errors. That's why it's easiest to use a calculator without having to go through steps hand by hand. We're going to do a hypothesis test. So let's read it together. In 1998, people who voted for a new park from a sample of 200 people were 95. In 2008, people who voted for a new park from a sample of 200 were 102. Is there statistical evidence that the proportion of people who want a park in the year 2000 is greater than that in 1998? Conduct a hypothesis test. Question, I put the steps down, and this would make it easier. You can use it as a blank template. So first we need to figure out whether it's a 1-prop or 2-prop test. So since they gave us 2 proportions or 2 samples, we'll say it is a 2 proportion z-test. It's a hypothesis test. Now we have to check conditions. If you decided to pause and do this yourself, that is perfectly acceptable, but you just need to remember to check conditions. It doesn't say assume conditions are met. So now let's check conditions. As I'd forgotten to state the conditions earlier when I was explaining hypothesis test, but you just need to remember that it's the same conditions as for a confidence interval. I'll put this in my solved notes, so it's my mistake. So for conditions, these are your conditions. It is the exact same, there's no difference. So now we're going to look at both SRS. I know I didn't say it in the question, so you can write that it's not given. So I'm just going to put it in the question. So from a random sample, and again from a random sample. So now I'll start with this one because otherwise the calculations will come out. So let's do as both SRS. So yes, and how do we know it's yes? We write given in the question. Now for independence, since we don't know for a fact, you'd say assume yes, and since we don't know the entire population, we would write the same thing, assume yes. So for now, this NP and all of this, right? We don't know whether it's approximately normal. That is not stated, we don't know. Now let's do this. So based off our sample, right? So what is N? N is 200 in all these situations. So if I were to make this, sorry, if I were to make another one, so you put 200 multiplied by the first one, which is 95, and then comma 200 times 200 minus 95, which is 200 minus 95 from here, comma 200 times 102, and then comma 200 times 200 times 200 minus 102 has to be greater than or equal to 10. So I made a mistake here. They're not 95. They're supposed to be your 95 out of 200. So 95 out of 200, 200 minus 95 out of 200, and so on. This is equal to 95. This is 105, 102, and 98. But this isn't sufficient enough for an answer. You have to calculate these values and show that they're greater than or equal to 10. Now, given that, we need to write down the formulas. So for a hypothesis test, the formula is, you need to start out in writing, is all of this. These are your important notes for a hypothesis test. So what is P1? P1 and minus P2 is something, some value. So since they don't tell us exactly what value, you equivalent it to 0. Now P1 minus P2, you said, before anything, you need to define what they are. So if we say P1, so that should be a 1, is proportion of people who voted for a new park in, let's say, 2008. And then accordingly, we will say P2 is the same thing, but for 1998. In 1998, and we'll close that. This is important because, that's important because this tells you what the P's mean. Otherwise, they could be arbitrary. You'd never be able to figure this out. Find P1 as 2008 and P2 as, there's a big formatting error. P2 as 1998. How would you propose we do the alternate hypothesis? Pause, try it out for yourself, or listen to me talk. So we know that these are equal to 0 firstly, right? The x's are equal to 0. So we say, is there statistical evidence that proportion of people who want to park in 2008 is greater than 98? So P1 has to be greater than P2. So this would be what we're looking at. So these all are not right. So we do that and greater than 0. If you wanted to, you could write as P1 equals P2 or P1 greater than P2 as long as you're consistent. Next, it's to find the z value. Since this question again, I'm just asking for a hypothesis test, you don't have to find it. But I put it in here so I want you to see what I'm talking about. So P hat 1 minus P hat 2 as defined here as P1, P2 again would refer to the same thing. So my proportion from the sample of 2008 minus 1998 minus P1 minus P2. This comes from your null hypothesis. You assume the null to be true. So this, as I told you much earlier, wipes out to 0. So z value, we don't need to find that in this. Now we just conduct the test. Now this is sufficient enough as your work, right? It shows that you know what you're doing. Now just conduct your test. I will put the picture of the TI Nspire as well to show what I mean. The pictures of what I had to type into the TI Nspire. So when I clicked on 2 proportion z test, this is what I had to do. When I put it into the TI, I let P1 equal to the 1998 proportion. So I put 95 to 200, and then my P2 I let it equal to my 2008, so 102 and 200. Now since I did that, this is P1 less than P2, which is opposite of what I did here, but in this case I let P1 equal to over there P2. Now this, again, similar to the previous when we were doing the confidence interval, this has a lot of jump. This is my alternate hypothesis. This is my z value if I had calculated it. This is my p value, which is what I'm looking for the most. This is my proportion, which is 95 out of 200, 102 out of 200. This is it's a different thing. We call it pooling, which we're not going to talk about. And n1 and n2 are just my sample things. So as you can see, this p value. Step 6 is to write down my p value. So I'm going to do that. P value 0.241939. Again, I'm going to round it down to 242. Now, is this less than 0.05? No. I'll delete this part so you don't get confused. So it is greater than 35. So we're going to write down here, since p value, right, p value, which is 0.242, greater than 0.05, then I'll put an arrow here. Then we copy this down. High p value, we fail to reject our null. Insufficient evidence that the proportion of people who voted for the park in 2008, right, which is this part P1, is greater than the proportion of people who voted for a new park in 1998. So that is how you would conclude. So this part is just the word format. So you have to write it in words. It is the word format of my alternate hypotheses. Or you could have just gone up here and copied this portion and put it into words and framed it. So you could have written insufficient evidence that the proportion of people who want a park in the year 2008 is greater than 1998. That's completely up to you. You can rewrite the question part of the question, or you could use the alternate hypothesis. Thank you so much for watching. This video did run really long because there's a lot to cover in it. Unit 6 will also run very similar, quite long as well. Thank you.